this is where the whole thing blows open. I mean, the whole thing where people have said we are 90, 99%, 98.5% the same as a chimpanzee. That's only when you're looking at less than 2% of the DNA that's in our bodies. So people need to realize this. Science changes, and then this being translated to the general public becomes much, much less. People don't want to talk about this with the general public because then we become wise to this, that, hey, the things that you taught us, the things that you said really don't have as much substance anymore. And what we're dealing with here is we're dealing with high confidence material because we can actually record the DNA. This isn't a bunch of speculation. We can see the regulation. Am I right on this, Rob? Well, hello. I'm here today with my friend Rob Stadler. I've interviewed him before on my podcast, but what we're going to do today is we're going to go through his new book called The Scientific Approach to Evolution. And if you are a Christian and you don't even like the discussions of evolution, hear us out. Hear this out. Hear Rob out and see what he has to say. And if you totally embrace evolution and you think it's silly to consider anything else, okay, well, hear us out and then make a judgment afterward. Let me just read a little bit about the background of Rob so that you get a sense of this. Rob Stadler earned his PhD in medical engineering from Harvard-MIT Division of Health Sciences and Technology. As a scientist in the medical device industry for almost 30 years, he obtained more than 175 U.S. patents, has more than 30 peer-reviewed publications, and has contributed to medical devices that are implanted in millions of patients worldwide. His experiences in gathering clinical evidence and in working in the Food and Drug Administration on the approval of medical devices, it prompted him to write this book, The Scientific Approach to Evolution: What They Didn't Teach You in Biology. And that's the topic of today's conversation. But I will mention he's also written another book, co-authored it, called The Stairway of Life, An Origin of Life Reality Check. So with that, welcome, Rob.
Hi, Jim. It's great to be here. Thank you.
You are a scientist. You're a medical device specialist. Do you believe in the physical resurrection of Jesus Christ?
Absolutely.
All right. And you think there's sufficient evidence for that?
Yes, I do, actually. Not scientific evidence I've uncovered myself, but it's out there.
I believe so too. I believe there's enormous historical evidence that points to the physical resurrection of Jesus Christ. So if anybody watching doesn't believe in the resurrection of Jesus Christ, send me an email to tour@drjamestour.org. And we can get together and I'll share that with you. So that's an invitation to unbelievers, only unbelievers, not believers, because I wouldn't have time. Now, what I'm going to do is I'm going to turn it over to Rob, and Rob's going to give a presentation. This is sort of summarizing what his book talks about, so you can get a more detailed version from his book. And Rob, I'm going to try to not interrupt you much. It's hard for me. And I'll only try to interrupt you if I think you're wrong on something, I'll call you out. But if I think it needs more clarity, I'll speak up. Or if I think that people that you're talking about have gotten away with much too much and you're being too kind to them, and I sometimes can't contain myself, but I'll try to minimize my interruptions.
You're welcome to jump in anytime. It is your channel after all, and I'm very grateful that you would have me on here, so thank you. Yeah, so you see the book here and the topic about, is evolution good science? And I want to start by broadening out a little bit here to recognize that we are right now in the midst of the information age. And every day here in the information age, you receive a deluge of new information coming at you from all kinds of sources. And surviving in this information age and not drowning in the information involves having a filter. And whether we recognize it or not, each of us has developed and honed and tuned our own filters, which is about accepting the information that you find to be truthful, that you trust, and then rejecting information that you don't trust. So each of us has these filters, and we're building on them and tuning them, and that's how we survive. But the question is, do you have the right filter for you? Because that filter really is defining who you are, what you believe, and how you perceive things. So that's kind of the big picture topic today, is about tuning this filter, particularly in the area of scientific evidence. In the world of scientific evidence, how do you know when you hear something tomorrow morning on the news, can I trust what they're saying, or is that kind of shaky, low confidence kind of science? And that's the big picture. But today we're gonna tune that in a little bit, focus on the topic of evolution and about evidence for evolution. Can you trust it or can you not trust it? And when I mention the term evolution, I'm talking about the big scale evolution here, which I'm sure we're all familiar with, where all of life today came from a common ancestor billions of years ago, a single cell, microscopic first life form that evolved into all life today. And that is quite in contrast with a simple reading of the book of Genesis, where God describes, instead of a single tree of life, he describes more of what I'd call a forest of life, where there are many different trees, and each tree is a kind of life. In Genesis chapter 1, the word kind comes up about 10 times. Like it does here in verse 24, God said, "Let the land produce living creatures according to their kinds, the livestock, the creatures that move along the ground, and the wild animals, each according to its kind." And it was so. And so I think we're pretty familiar with things like the dog kind, or canine, wherein wolves over time have diversified to produce all the breeds of dogs that we know and love today. But they're all still dogs. They're all still part of the dog kind, and they're on this tree, this single tree of dogs. And so the scientific question then is, which of these two hypotheses, the tree of life or the forest of life, is supported by science? Which one has the most evidence for it? And to just dip my toe in that a little bit, to just get started, I'd like to suggest that science, because of my practicing science for 30 years, science is so much about observing what you observe and how your observations teach you about natural laws, about how natural laws behave and what they do and what they don't do. And so that observation process requires a human there to be able to make those observations and to pass the learnings along to the next generation. But of course, over here on this tree of life, humans only existed for a pretty short period of time here in history. And beyond that, going back in the past, there really are no direct observations that anybody could have passed along. And that's not to say that science has no place back here, that science can't say anything. But what science has to say back here in the past is more tenuous. It is lower confidence kind of conclusions you'll come to compared to what you have here in the more recent time. And it's interesting when you compare the tree of life here under that view to the forest of life, you end up with almost the same exact picture. In other words, what humans have observed in our history and passed along is pretty much in agreement with what the Bible describes in Genesis.
If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus.
So we're going to go in a lot deeper into this, into what kind of evidence we have for evolution and what kind of evidence provides more confidence. But I just wanted to give that as a little foretaste of it. So according to science, we're trying to answer the question, which one of these two has more evidence? Which one can I trust in? And so being a good scientist, what you want to do is take these two hypotheses, gather evidence, and pile up the evidence and weigh it out and just determine which of the two hypotheses has more support. And then you need to keep an open mind and follow the evidence where it leads. And someday the evidence may change over. Some new evidence shows up. Well, you have to keep an open mind to that. And so that's what I'd like to do here. And to start off, I think everyone listening will know and agree pretty well that most scientists today say that the evidence in favor of evolution, the tree of life, is overwhelming. And scientists in biology books and all kinds of media will tell you that. And basically, they'll say only a fool would disagree with that conclusion. And this is my son's high school AP biology textbook, and it's very clearly written in piling up evidence on the side of evolution. But there's two challenges to that. The first challenge is that these sources of information, they will only speak about evidence in favor of evolution, and they basically forbid or block out any discussion about the alternate hypothesis up front. And that actually is a very strong form of bias. It's kind of the worst kind of science, is when you block out the alternate hypothesis up front and you don't even allow it to be considered. So that concerns me right up front. But the second concern is that and this is what we're going to dig into with the book I wrote, is that they're actually, in the end, they're prioritizing weak or low confidence kinds of evidence over stronger forms of evidence or high confidence kinds of evidence in order to make this conclusion. And I find that very concerning. And I'm going to first dig into what do I mean by weak evidence or strong evidence. And I'm going to use my own area of study, medicine. In medical research, I think I can argue medicine is like the most valuable application of science to our society, because medicine determines life or death. When you take a pill or you go through some medical procedure, your life is on the line. And so you expect that good science is behind, what you're undergoing, or else you shouldn't trust it. You shouldn't trust your life to it. So in response to society really demanding good science behind medicine, now I'm not saying it's perfect, of course. There are mistakes made in medicine, but I'm saying society demands really good quality science behind medicine. That led all doctors in all countries to agree upon a categorization of evidence, levels of evidence. And that's shown here. So all doctors will agree on these levels of evidence, that if evidence in favor of a drug or in favor of some procedure is up here in level A, then that's considered quite strong evidence that justifies going ahead and prescribing that drug or something like that. And so forth down the line. We don't have to go into the details, but it's interesting to note that the lowest level of evidence here is called a consensus of expert opinion based on experience, based on their clinical experience. So expert opinion is actually considered not very strong here. What you really need is a randomized controlled trial in the field of medicine to convince people that this therapy is beneficial. Now, I wish that all forms of science had this kind of levels of evidence that are agreed upon, because I find in some areas of science that evidence is somehow all considered the same. Evidence is evidence, and there's not a clear way to stratify it like you see here. And so in the book I wrote here, I proposed 6 criteria to determine the level of evidence, and this is for all science, not just medicine, any field of science. And these 6 criteria, I've never actually had anyone debate them with me. People generally agree that these criteria, maybe there's plus or minus 1, 7 criteria, 5 criteria, but they all seem to agree that these criteria do determine the level of confidence you can have in scientific evidence. And this is helping you to determine your filter. Remember the filter of information that we all have. Now, these criteria are not exactly like black and white, right? It's actually kind of a spectrum of confidence you can place in a scientific result. It could be high, medium, low, so forth. But I'm going to go through these 6 criteria and give you a feel for what I'm talking about. Hopefully these are kind of obvious to you. Number 1 on the list of 6 is repeatable, right? If you have an experimental result or any kind of result and you can repeat it again and again, naturally you're building confidence that this is high confident result. And if someone else can repeat the experiment, get the exact same answer, that certainly gives you more confidence. And if somebody in another country can do it, even more confidence. So that one's pretty obvious. Number 2 on the list is that things that are directly measurable give you more confidence than things you can only assess very indirectly. Let me give you an example there. When I was a kid and I told my mom I wasn't feeling so good, she would come to measure my temperature, and she tended to do this indirect measurement of measuring my temperature, and she'd say, "I think you have a fever or not." Of course, that doesn't give you as much confidence as the direct measurement. I think we can all agree on that one. Direct measurements give you more confidence. Another example of this would be if your goal is to study black holes out in outer space. Black holes, of course, you can't actually make direct measurements on them, and you can't bring it into your laboratory and poke it and prod it and study it that way. And so what we know about black holes is all through indirect kind of results, and that makes it a lower confidence kind of finding. So that's number 2. Number 3 on the list of 6 is to conduct your studies prospectively. And what that means is that you plan the study in advance, and then you conduct the study, and you find out what it says that way. This is in contrast to looking back in time, looking back at data that you've already collected previously. That's a retrospective study. And the benefit of doing it prospectively is that you can design your experiment to control for things that might confound your results. So let's say I'm doing an experiment where I want to just simply study how fast an object falls. When I drop something, how fast does it fall? I can prospectively design that and prepare the study to block out any kind of confounding factor, like, for example, the air in the room. The air in the room has an impact on how fast the object falls, especially if it's very windy, something like that. So I can plan the study to get the air out of the room and have a more controlled situation that gives me a more confident result. Number 4 in the list is to avoid bias. And bias is just devastating for science. I think any scientist would agree with me on that one. And we all have bias. I have bias. Everybody has bias. And we want to avoid bias in order to get to the truth. Bias is kind of like glasses that you're looking through because you perceive everything through your bias. And that can taint the results and cloud the truth. Now, when I do a clinical study for my work, I actually have to have a section of the protocol that I write that describes how I'm going to actively avoid bias or try to exclude bias from the study. So it's not good enough to just say, I'm going to try to not be biased. You got to actually take steps to try to avoid bias. And in clinical studies, we've probably heard of the concept of double-blind study, right, where the doctor doesn't know what drug you're getting and the patient doesn't know what they're getting, and that gets rid of quite a bit of bias in that sense. Number 5 is to avoid assumptions. Assumptions are kind of like shortcuts, and when you're doing science is hard to do, and naturally you look for ways to save money or save time, which almost always means taking an assumption, and that can be costly. They can really come back and ruin the whole result. So back to the experiment where I'm just going to drop an object and see how fast it falls. I mentioned that the air in the room is a confounding factor, right? That's going to mess with my experiment. But I'll tell you that in order to pull the air out of the room is going to cost me 6 months of time to build the equipment. It's going to cost $1 million. And so I'm really eager to try to make the assumption that the air just doesn't matter or it's insignificant. So these kind of things happen all the time in research, but the important thing is that you openly disclose the assumptions you make and you provide a decent justification if you're going to make that assumption, and then people can decide if that was a reasonable, justified assumption or not. But the worst thing you can do is hide your assumptions and pretend like they don't exist, and then you're going to get in real trouble. And then the last one, number 6, and this is more about how you summarize your results, and it's about making reasonable claims. You don't want to make claims that are above and beyond the conditions in which you did the work. And I like to use this analogy here of a can of nuts. You could buy these nuts right now today, but the people who make these nuts, they really want you to buy lots of nuts. And so they want to make some claims here to get you interested in that. And one of the claims they make is that these are heart healthy and that the American Heart Association certifies them, making you think that eating them is going to make you live longer, so forth. But we have the Food and Drug Administration here, the FDA, and they make sure that claims are validated or are supported. And I think they required this little statement to be put on the can of nuts. Here it is. It says, scientific evidence suggests, but does not prove, that eating nuts may reduce the risk of heart disease. And I really appreciate this. It's a little awkward, I know, but I appreciate it because you see these hedging terms here. I think they're really honestly giving you a candid feel for how much evidence they have and what that evidence really has to say. They're not making some strong claim like if you eat these nuts, you'll live forever, or this will save 10 years from your life or something like that. This is reasonable. And that's number 6. In contrast to that, this would be my son's high school AP biology textbook, and it makes this statement. For example, organisms as dissimilar as humans and bacteria share genes inherited from a very distant common ancestor. So you note that this statement has no hedging terms. It doesn't say we think or evidence suggests or we believe or it may be. This is very directly exuding confidence, a certainty, you would say. But we'll get into it later about what's actually behind this statement. But I don't think the level of confidence that it's conveying is appropriate for the evidence that they have, as opposed to this statement made about the nuts. So we kind of have to ask, why is our society more concerned with claims made about nuts than about claims made about evolution? The textbooks can go forth and kind of ignore this make reasonable claims criteria when they write their textbook and teach our children. I find that concerning. So we've gone through these 6 criteria that tell you if you have high confidence or low confidence in something. And I hope that this is useful to everybody as a kind of filter, like I mentioned, when you get new information coming at you tomorrow, some of that deluge of tomorrow's information, that you'll be able to filter out things that you can have confidence in versus things that you can't. I could summarize it with going back to that example of, we talked about how fast does an object fall? It's a very simple question to ask of science. But I'm saying that if you conduct your experiments with meeting all 6 of these criteria, and it can be done to meet all 6 of these criteria, you're going to end up with answers that are very high confidence. You can put total trust in what you've got there, and people will use it, and it could be very helpful. In contrast to that, I'm going to put up the statement that I just read there. This is from my son's biology textbook. And it's addressing a different question. It's addressing the question over here. Do humans and bacteria share genes from a common ancestor, right? This goes back to that tree of life. And this statement in my kid's biology textbook is very strongly asserting, yes, they do share genes from a common ancestor. But if we ask science this question, can we answer this question while meeting these 6 criteria? Can it be done repeatably? In other words, can we repeatedly go into the lab with an organism and watch it evolve into bacteria and into humans, and definitely seeing that we have repeatedly made humans and bacteria from it? And of course, that can't be done. It's just simply not possible. Can it be directly observed? I kind of mentioned already, you can't observe this happening. Certainly nobody ever witnessed this happening. Can it be studied prospectively? Well, it's kind of the same answer. You can't go into the lab and do that. In fact, it's an extraordinarily retrospective study, if anything. Can you avoid bias when you try to answer this question? I think this question is just ripe, full of bias. People come at this with a very strong answer already before they even consider the science. There's plenty of opportunity for bias here. And in fact, I think the bias can swamp what the evidence actually has to say, because the evidence is pretty quiet here. And number 5, are we careful to avoid assumptions? I think this entire statement up here from my son's biology textbook is based on an assumption. Basically, they're assuming that if I have a gene and bacteria has the same gene, then the only explanation for that is that there was a common ancestor. That's how we end up with the same gene. That isn't proven, again, because we haven't been able to observe it or test it, but it's an assumption. And so I think the entire statement is based upon an assumption that they're not stating up front. And number 6, overstated claims. We already kind of talked about that. This has no kind of hedging language, anything in it. It's exuding confidence that actually doesn't exist. So this statement belongs way over here on the left in the very low confidence bin because it fails all 6 of these criteria. In contrast to something like this, which you can just really nail it with science to get the right answer. So I hope this kind of thing is helpful, going forward from today when you hear things on the news tomorrow about some new scientific finding, like something found on Mars or some new drug for cancer. You can put this into practice. So getting back to our question of focus here, which is we have these 2 hypotheses, and according to science, which one of these 2 has stronger support? And we're going to gather the evidence and weigh it out and see what we got here. So what evidence do we have in support of this tree of life? What's the best evidence we have to support this? And if you look at biology textbook or you look at any kind of media on this topic, books by Richard Dawkins or anyone else in this area, generally they'll categorize the evidence into these 4 categories. I think we're all familiar with the fossil record. They claim that is in support of this tree of life. Geographic distribution, it's a topic like why don't we have penguins here in Minnesota? Why are animals distributed around the world the way they are? Vestigial organs like your appendix, probably familiar with that, is seen to be evidence in favor of this tree of life. And then comparing different life forms, that also involves the statement I just made, but it's about saying, like, my arm has 1 long bone in the humerus, and then it has 2 long bones below the elbow, and then 5 fingers. Well, it turns out that reptiles and dogs and bats all have that same arrangement in their appendage. And so because they have the same arrangement, that suggests that we came from a similar common ancestry. And just to summarize this a little more clearly, I'm gonna phone a friend here and bring up a short video from Richard Dawkins, where he is asked this same question of what's the best evidence we have for evolution?
Out of all the evidence used to support the theory of evolution, what would you say is the strongest, most irrefutable single piece of evidence in support of the theory?
There's an enormous amount of evidence from all sorts of places, and it's hard to pick one strand which is more important than any other. There's fossils, there's the evidence from geographical distribution, there's the evidence from vestigial organs. I think, to me, perhaps the most compelling evidence is comparative evidence from modern animals, particularly biochemical comparative evidence, genetic, molecular evidence.
Because of you, millions of people have heard the gospel. If you confess with your mouth Jesus is Lord and believe in your heart that he's risen from the dead, and you will be saved. That's right. That's the requirement. We talk about science concepts which draw people in. Take these nanomachines and have them drill into cells. This would be a great way to kill cancer, right? We also talk about Jesus Christ, who's the best in everything. My faith in Jesus Christ means more to me than anything. If you could continue to give or give for the first time, we would certainly appreciate it. You can go to jesusandscience.org. Thank you so much.
Okay, so you heard it directly from him. This is the evidence he has. And what is the best form of evidence he's got? And that would be a comparison of life forms, comparison of the genetic similarity between life forms is the best evidence he's got. The problem is that the statement that we just analyzed rather carefully here, this statement is about comparing life forms, finding similar genes between humans and bacteria. And we just went through that and determined that it meets none of these 6 criteria for high confidence. In fact, it's the lowest of low confidence. And yet, Richard Dawkins says that is the best, the most compelling evidence that I got. It doesn't get any better than that. And that's from his own words. And so I didn't go through all the details about the fossil record and geographic distribution and all that, but it's in the book. But all of those forms of evidence, when you compare it against these 6 criteria, they fail. Every one of these criteria, all of this stuff is very low confidence evidence. And it surprises me that our children aren't given consideration of that in schools. And they're basically just fed this as the only evidence that there is, and it's overwhelmingly supporting this tree of life. So we're left to ask, is there any high confidence evidence for evolution? Is there anything out there that's better than this? And maybe it'll surprise you that there is high confidence evidence that deals with evolution. And this is one example. Richard Lenski, a professor at Michigan there, he spent his whole career studying E. coli, the bacteria, growing them in his laboratory. And he's actually gone through 80,000 generations now. He just surpassed that, studying how they change over time with 80,000 generations. He does about 6 or 7 generations per day. Fortunately, E. coli, replicate faster than humans, quite a bit. Now, quite interestingly, after 33,000 generations, so this is about 10 trillion organisms he had produced in his lab, the E. coli there developed the ability to eat something, to get energy out of a food source that they hadn't used before, is a molecule called citrate. And that was in the media that he bathed the bacteria in each day. And so these E. coli that developed this ability, they suddenly, replicated much more readily and took over the population. And this was considered to be a big evolutionary feat. In fact, in The Greatest Show on Earth, a book by Richard Dawkins, he spent like a whole chapter talking about how great this experiment was. And he called this finding a beautiful demonstration of evolution in action, with new information entering genomes and combinations of new genes. So there was a lot of media hype about this. Unfortunately, Richard Dawkins made this statement and wrote this book, published it, before the actual genetic information came out about what had changed after 33,000 generations. So Richard Lenski's lab, he had these 2 papers come out, and these 2 papers showed exactly what genetic changes had happened. And it turned out that the ability to metabolize citrate involved duplicating one existing gene, simply took a gene and made another copy of it, put it down somewhere else in the DNA. And then another gene, the bacteria lost control of it. It lost its ability to regulate that gene. So that's actually a loss of information. And those 2 mutations led to this evolution, if you will. And so I think Richard Dawkins was quite misled in his conclusions, which came out before the real data came out. But this study shows us, it gives us quite a feeling for what evolution can accomplish, what it's capable of accomplishing in quite a large number of generations. And I need to highlight that all of that was high confidence kind of work. It's repeatable, it's directly measurable because you can sequence the DNA in the genes. He actually froze samples of the bacteria, and you can bring them back to life and repeat the experiment. And it's prospectively studied, all those things.
So wait a minute. Let me. When he froze them, it wasn't like he brought them back to life. They were never dead.
That's right.
He brought them back to life, right? So
right.
it just goes into a dormant state.
Yes.
Correct. I just want to be sure because
Yeah.
I didn't
exactly
think anyone
right.
ever's brought something back to life. Okay.
Yeah, so like this happened, he would save off and freeze like every 500 generations. He would freeze a sample of these bacteria. And so when this happened, he actually went back to frozen previous generations and was able to get them, to go through this kind of transition as well. So he could repeat the experiment, is what I'm saying, by having frozen it
Right.
in time.
And once you have bacteria that have this genetic change, bacteria are amazing because they share DNA with each other. And that's how you can get the ones that were frozen. It doesn't take them as long to acquire this. They got it very quickly from their neighbors. Is that correct?
Yeah, they share genes. Yeah, it's kind of like sharing information with your friend on how to do your taxes or whatever it is. That's what
Yeah.
bacteria can do.
Yeah.
And just to add a little more color to this, it turns out that E. coli have always had the ability to metabolize citrate, but they only metabolize it when there's no oxygen around. So if he simply put these bacteria in an environment without oxygen, they would have started eating the citrate. But these bacteria here, these E. coli in his lab, developed the ability to metabolize citrate in the presence of oxygen, which, as I say down here, is actually a result of losing control over a gene that was there to trigger when oxygen was not available. So that's kind of interesting. So another experiment, this is, again, high confidence evidence for evolution to get a feel for what evolution can accomplish. I love this experiment. You can see it's written up down here. But they actually purposely studied what evolution is capable of. They took E. coli, again, our favorite little bacteria. E. coli are able to produce their own amino acid tryptophan, shown here, because they have the machinery to make their own tryptophan. They have this enzyme, tryptophan synthase. And humans can't do this. So it's kind of a cool trick that E. coli can do that. Anyway, they took in the genes to produce this enzyme, they went in and intentionally damaged the DNA there to see if evolution could come in and repair the damage to get the bacteria back to having this function. It's kind of a cool idea. So in their first experiment, they changed just one nucleotide, one letter of the DNA, and that was a part of one of the two genes here. And they found that the enzyme still had some function to make tryptophan, but it was not nearly as high performing as it used to be. And then they put that mutated bacteria into a solution that had a limited amount of tryptophan, because they want to create some selective pressure here. That it would sure be nice if you could make your own tryptophan and then you could take over the world, right? And so they did that experiment, and they kept growing more and more bacteria to see if they could redevelop the ability to fix this gene. And what they found was, after about 100 million E. coli were grown in the lab, the mutation was in fact repaired. Apparently a random error in copying the DNA turned out to be beneficial, right? It fixed the gene. And the E. coli with a fixed gene had a big benefit, and they took over the population because they could make their own tryptophan. That's pretty cool. So evolution did the job. So they said, let's do it again, and they changed a different single letter or nucleotide of the DNA code for the same gene, but it was in a different location. And this time, the enzyme had no function, right? It was completely not functional. And they grew this mutated version in a solution with limited amount of tryptophan. And they found over time that, again, pretty much same answer. The E. coli were able to fix that 1 point mutation, and they were able to make their own tryptophan and took over the population. So that's 2 successes. Evolution was able to do that. And again, this, just to step back for a second, this meets all of those 6 criteria to give you high confidence. They could do it repeatedly. It was done prospectively, direct observations of the DNA, and the results came out of it. It was beautifully done. So then they said, okay, let's see how far this can go. So they did a third experiment where they made both of the mutations. So there were 2 hits to the DNA, 2 point mutations, and the enzyme had no function. And their thought was that if the bacteria could fix the one problem and get a semi-functional enzyme, then over time it could fix the second problem and get back totally to normal. That was the hope. But after 9,300 generations of E. coli were grown, and that's like 1 trillion organisms they had to go through there, they actually found out that the function of the tryptophan synthase was never restored. And it turns out that the genes, when they looked at the DNA, the genes were either completely deleted or their function was suppressed. The regulatory aspect, it just turned off expression of those genes. And that's because it actually takes tryptophan to make this enzyme. And so if there's a limited amount of tryptophan, maybe you're better off just not trying to waste it, make it. And that's the direction that this E. coli took. So just to try to summarize this very easily for everybody, you have a mutated bacteria. It had these 2 mutations, so it could not produce tryptophan. And it really could have gone in 2 different ways. The bacteria could have taken the easy route, just stop producing that enzyme or jettison the genes for that enzyme and just take life easy, or it could have evolved by fixing those genes and having all the tryptophan it ever wanted. But it actually took this route, and this was in 12 repeated experiments. It went this way. So that kind of leads to a big question, that if evolution failed to repair this enzyme, the strip of DNA with 2 genes, and it was already 99.9% totally accurate. In other words, there's about 2,000 nucleotides in the code to make tryptophan synthase, 2,000 nucleotides, and they only had 2 mistakes. So it's 99.9% just perfect. And evolution couldn't fix it. It actually went the other way and gave up. So how could evolution ever have come up with that gene, those genes, out of nothing if it couldn't have evolved it from 99.9% finished product? I think that's very telling. It's telling us with high confidence what evolution is capable of and what it's not capable of. And then I'll just throw in a few more little tidbits of high confidence evidence for evolution. We as a society have been studying mice for like 95 years and doing every kind of mutation imaginable. This poor little guy on the right, actually you could see has 6 limbs. They made some mutation in the mouse that caused the gonads to become extra limbs. So they have 6 limbs, very interesting. But the point is, after 95 years of doing that, there's 2 outcomes. You either end up with a mouse or a dead mouse, meaning that mice want to stay as mice. There's nothing dramatically changing going on here. And the same has occurred for endless studies of fruit flies and zebrafish and domestic animals like your cows and your dogs and so forth. They stay within their kind. We've seen that. And then I bring this up because it's a very recent study. It's just last year, but these people have been studying for 10 years. They studied the genome of this little microcrustacean. And basically they summarize, these are their own words, but after 10 years of watching evolution work on it, they saw an average effect close to 0, meaning that nothing really changed. So this compilation of evidence, this is all high confidence evidence meeting those criteria that I mentioned. And what it's telling us, I think what it's very clearly teaching us, is that evolution is quite limited, quite constrained, and quite weak in what it can accomplish. Now, at this point, I almost always get a question that I thought I'd address up front, and that is about the COVID virus. Because we've all just gone through this epidemic, and in the last 5 years, we've seen quite a lot of changes happen in COVID. A lot of people talk about evolution, rapid evolution of the COVID virus. So what about that? I mean, this is high confidence stuff, right? Because we've observed it and it's prospective and it's repeatable. So it is indeed a fact that about 100 mutations have accumulated in the last 5 years. If you take COVID virus today and you compare it to the original start of the pandemic, there's about 100 mutations in there. So that's a lot going on. But there's some reasons why I feel like it's going against the criteria number 6, where you make the right kind of conclusions, you draw the right kind of conclusions. Because using this data to conclude that living organisms should be able to evolve rapidly. I think that's a bit of an abuse of the evidence. And the reason why I say that is viruses like COVID are really well known for frequent recombination, meaning if a cell is attacked by two different viruses, they go in there and they just sort of share notes with each other, the two viruses. They can share DNA and swap parts, kind of mix and match their RNA or DNA in order to make a new virus very quickly. That's part of the thing. Another part of it is that the COVID genome is all RNA based, and it's about 30,000 nucleotides of RNA, which is quite small, really. You know, this is about 5% of the size of the genome of the most simple bacteria. So it's really, really small. And because it's RNA, it is replicated through an RNA polymerase. So that's a protein enzyme that has to be manufactured by the cell that it's attacking. And this process of copying RNA to make copies of itself, to replicate, it's quite error prone. It produces about one error for 10,000 nucleotides that it replicates. I know that sounds pretty good, actually, 1 out of 10,000, but in life, that's really bad, because any known living organism, and I'm very clearly saying that viruses are not living organisms because they don't have a metabolism and they don't have homeostasis and they don't have to harness energy and they don't have to repair their DNA and so forth. They completely rely upon other life to do that. So any living organism that we know of, the replication of DNA there is about 1 error for 100 million. So this is 10 to the 4 orders of magnitude different in errors, to tell you how sloppy the RNA replicase is for COVID. So my point is that compared to living organisms, COVID can make changes very quickly, and COVID has very few responsibilities, let's say. I say here it can throw caution to the wind. What I mean is that COVID really has only 2 jobs. One job is to get into a cell, and that's what these spike proteins are for. And the second job is to take over the machinery of the cell to replicate itself, lots and lots of copies. So that's the only 2 responsibilities it has. But the cell that it's attacking, you know, with all of its DNA and all of its genes, right? It has hundreds and thousands of different jobs that it has to do the energy harnessing and the metabolism and the membrane, all the stuff that life has to do, replicating all of that. So COVID basically can do whatever it wants and throw caution to the wind and change rapidly, and who cares? And that's basically what's going on here. So my point is that applying this to evolution of living organisms, even bacteria, simple living organisms, I don't think that's a fair thing to do, to claim that living organisms should be evolving kind of like COVID has taught us. Viral evolution is a very different, very chaotic and unconstrained kind of process. So I thought I'd throw that in there as a recent example. Okay, so looking at the data we have now and focusing on the high confidence evidence for evolution, these high confidence evidence experiments are all pretty similar in that you take an organism and over time you give it this selective pressure because you want it to either change or die, right? It's under heavy selective pressure, so it's going to change or it's going to die. And you keep doing that to see how much you can get it to change over time, and that's evolution. And because it's high confidence work, we can look at the DNA at the end of the road, and we can look at the DNA that we started with, make a comparison and say what exactly has changed or evolved here. And we can have quite high confidence in what evolution can accomplish or what it can't accomplish. And what we found then is in that study by Richard Lenski, took about 33,000 generations to have these 2 mutations show up. And in the study of tryptophan synthase, they went through 9,300 generations, and that was not able to repair 2 point mutations. So we get a feel for what we can accomplish with evolution here. So the question for me then next is, what if we apply what we learned about evolution, apply it to this scenario here, which we're all familiar with? Can humans and chimps have a common ancestor that evolved over, say, 6 million years? And to do that, we have to know what are the differences between humans and chimps, or the common ancestor. How different are we? Looking at the DNA there, the answer lies in what's called orphan genes. And if you'll excuse this bad joke, orphan genes are genes that one type of species of life has that no other species has a gene like that, meaning a gene that's even similar or close to it, that can be related to it. And I like this summary by a New Scientist, where they said that when biologists began sequencing genomes, they discovered that up to a third of genes in each species seemed to have no parents or family of any kind, meaning that they can't see a common ancestor for that gene. You know, when we talk about evolution, they always talk about the common ancestry and shared genes, but they don't tend to talk about genes that are unique. Like my kid's biology textbook, it doesn't talk about these kind of orphan genes. It doesn't mention that. But every living thing is carrying around some genes that no other species has. So where did they come from? With no obvious ancestry, it was as if these genes had appeared from nowhere. But that couldn't be true. Why does she conclude that couldn't be true? Because she's starting with the assumption of common ancestry, and of the assumption that no one was involved in designing our genome.
And she's probably starting with bias, right?
There's some bias there, exactly, which is dangerous. So everyone assumed that as we learned more, meaning that as we started sequencing more and more different species' genomes, we would discover what happened to these genes, where they came from. But we haven't. Quite the opposite, in fact. And in fact, if you take like all of the genes found in all of life, and you pile up the genes that are similar, shared between different species, and then you pile up the genes that are orphans, and each orphan is a new thing, right? And so you pile those up. There are in fact many more orphan genes in the library of world genomes than there are shared genes. But surprisingly, our textbooks don't talk about that. So between human and chimp, this paper said there were about 1,418 genes, is what they found, that between human and chimps do not have orthologs, meaning there's no similar looking gene in the chimp genome. So where did those come from? And I found it really interesting. I pulled this out because Jerry Coyne wrote this book, Why Evolution is True, where he gave his best argument for the tree of life and common ancestry and why evolution is true. And I was quite surprised that he stated this. He agreed with it and copied it, that 6% of genes found in humans aren't found in any form in chimpanzees. So he, of course, must believe that those just evolved. But, you know, we just went through what evolution is capable of. You know, it's capable of a few point mutations, fixing a few mutations over time. But here we're talking about, you know, over 1,000 different genes. And this is over a number of generations that's kind of getting close to what Richard Lenski has studied in his bacteria. So I think that should make people wonder if, in fact, this doesn't make a lot of sense. And it's not a God of the gaps argument. This is an argument from what we know evolution is capable of and what it's not capable of.
So can I ask you something about this? If you go back to that 6% slide.
Yeah.
Yeah. So hold there for a second, because, and tell me if I'm speaking low confidence information. or if I'm speaking high confidence. This report came out in 2006. Then he's writing it in his book, which came out in 2009. So there's a 3-year gap there, not much. It takes at least a year to get a book published. But since then, in the last 19 years since then, hasn't that 6.4% gone way up? In other words, through Project ENCODE, there's a lot more discovery that many do not have orthologs. Or am I wrong on that?
Yeah, there's certainly a lot of controversy in settling on a number here. And some would argue that it's extremely hard to quantify the difference. So I can't give you an answer. And to be honest, there's also debate over what a gene is nowadays. The concept of a gene was a simple concept when it was proposed, but now the more we learn about genes, the more we recognize that we don't really know what it means anymore. That's probably a topic for another discussion.
Yeah,
but
and let me just explain to people what you just meant, because normally one looked at a gene and said that defined through RNA making of a protein that would build something on your body. But now we understand that a lot of genes, a lot of the DNA serves as a regulatory function. It says, what am I going to turn on? What's going to be turned on and what's going to be turned off? So in other words, it's not coding for a little nanomachine protein that's going to build your body, but it's saying you get to be built and no, you don't get to be built. It's more of a trafficking thing. And so I think that's what you mean by the definition of a gene. Have I got that right?
Yeah. I mean, people used to only think of genes as, like you said, producing a protein. And now we see it much more broadly. And some only produce RNAs. They're sometimes referred to as non-coding pieces of DNA, but they actually are producing RNA and having quite an impact on a living thing. But we had too narrow of a view of it in the past.
Right. And so, again, correct me if I'm wrong. My numbers may not be up to date. But if we were, of our protein coding genes, the ones that code for proteins, that's what people used to speak about when they said that we are 98.5% the same as a chimpanzee. But they discounted what they called junk DNA. That has gotten a new term. The junk DNA is no longer called junk because people have seen it's not junk. It's called intergenic DNA. And that DNA, that intergenic DNA, it was believed didn't have any real function because they weren't protein coding genes. But it turns out that they have regulatory function, and a good portion of that 98.5% of the DNA in us turns out to have regulatory function. I don't know what percentage. I thought you had said as much as 30%, which would mean it's much more content than the protein coding genes, which is very different than that of a chimpanzee between a human. Am I getting this right, or am I functioning on an outdated knowledge?
No, I believe the protein coding genes are only 1 or 2% of our complete DNA.
Yes.
So the rest of it, the 98% that isn't coding for proteins directly, used to be considered junk. And now we recognize that that's really where the treasure is. And that's where a lot of the differences exist between humans and chimps.
Yes. So we got to be clear here, Rob. This is where the whole thing blows open. I mean, the whole thing where people have said we are 99%, 98.5% the same as a chimpanzee. That's only when you're looking at less than 2% of the DNA that's in our bodies. When you look at the other 98% of our DNA that's in our bodies, you see vast differences between us and the chimpanzee. And so it was like this secret that just got exposed through ENCODE. And at first they thought, oh, well, okay, I'll give you a little bit. But it turns out again and again. And each year they were finding more and more among the intergenic, the formerly called junk DNA that has this regulatory function. So these are the traffic cops that allow things to go and not go. And so this is what turns on. And we're so different. And so people need to realize this. Science changes, and then this being translated to the general public becomes much, much less. People don't want to talk about this with the general public because then we become wise to this, that, hey, you know, the things that you taught us, the things that you said really don't have as much substance anymore. And what we're dealing with here is we're dealing with high confidence material because we can actually record the DNA. This isn't a bunch of speculation. We can see the regulation. Am I right on this, Rob?
Yes, I totally agree. And to put it in perspective, when you said vast differences between humans and chimps, some of that is because of just the immense size of the genome. When you have 3.2 billion base pairs of DNA in a human, 6% of that is indeed vast. It's a huge amount of DNA, 6% of 3.2 billion.
No, but also you're not being fair, Rob. You're not being as hard on these people as they deserve, because you're saying 6%. That's a number from 2006. In the last 19 years, I think there's been a lot more that's been exposed. Now, I may be wrong on that, but I think that Project ENCODE is finding more and more in the last almost 20 years. And so that number of 6%, you're being very gracious. You're not being fair in telling us that number is probably actually much higher. Do I have that right? Again, I'm not an expert in this. I'm deferring to you.
Yeah, there is tons of debate over that topic of what the percent difference is. But I think where there's general agreement is that when you take 3.2 billion times even a few percent, you get massive differences, which compared to what we've seen, bacteria can change over time. It's like a millionfold what we would expect to have happened to get a human out of a common ancestor with a chimp. Millionfold difficulty compared to what we've observed. That's what I get to. So let's bring this whole thing back together now. This is closing it down. So according to science, which of these is correct? We have one hypothesis, tree of life. Another hypothesis is more of a forest of life. And I think the argument I'm making here then is that only some low confidence evidence, if you want to follow Richard Dawkins and get excited about the evidence he presented, which meets none of the criteria for high confidence, that's what's being taught to our kids. That's what every high school is teaching. But I think it's clear that
it's not just high school. It is advanced college. It is graduate students are learning exactly that as well.
Yeah, and it scares me, really. So, I mean, the high confidence evidence is vastly opposed to the tree of life, is the point. And like I said, if you're a good scientist, you follow the evidence where it leads, and things could change over time. We're open to that. But I'm telling you, this is where the evidence stands here and now. And maybe this shouldn't surprise us, because God told us this is going to happen right there in Romans chapter 1. For since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made. In other words, just open your eyes and look around, make your observations, and it's pretty clear that God is behind it. And men are without excuse. For although they knew God, they neither glorified him as God nor gave thanks to him, but their thinking became futile and their foolish hearts were darkened. And that's what we're facing. So I'm going to just wrap this up. These are the two books that Jim mentioned that I've worked on. And, Jim and I've talked a little bit before about the origin of life, which is, of course, his big focus. And this book about the origin of life, I think, is relatively easy to digest. But to make it even easier and more palatable, we've converted it to a series of YouTube videos that are animated And you can find those by looking for Long Story Short, The Origin of Life. So thanks for your time. Appreciate it.
All right. So Rob, you've got these two books. Yes, The Stairway to Life, which is the origin of life, which is an area that I've studied a lot in the last 6 years, and I know so many of the fallacies that people have put forth. I have not spoken that much on evolution because, I know more of the chemistry than I do of the biochemistry. And so I've tried to stay in my lane in that regard. Although chemistry is the basis behind biochemistry, hence the term biochemistry that contains the word chemistry. And this is what you're talking about today. I mean, I didn't know anything about origin of life studies 7 or 8 years ago, and I learned about it. And one day I might step in the evolution waters and take that down too. But right now I'll leave it to you, and I'll just build upon this. But I think one of the topics that I want you to talk about for a minute or two is this squishy word called evolution. People look at it in different ways, and I think you touched on this in your book. Because before this podcast, I read the book, but it was a couple of weeks ago, and between finishing your book and right now, I've read a couple other books, so I'm kind of mixing up who said what. But this squishy word, I mean, some people, by that, they mean this gross anatomical body plan changes, say from some common ancestor to where we are as human beings. And other people mean just small modifications, as you might see some genome changes in a bacterium due to stresses from the outside, epigenetic, or just random changes that might happen. So talk about this because certainly we see evolution occurring in small changes. I work with bacteria. I don't personally. I have people in my laboratory that work for me that work with the bacteria. And we can go through multiple generations and see modifications in their genome. These are small modifications that you see, and there's no contest on that. That is high fidelity, high quality determinations. But then the other thing that people talk about, and they'll mix the two terms. One is high value information. The other, in your terminology, would be low confidence information. Touch on that.
I hear you very much. I think there's some bait and switch going on often, because they'll give some high confidence evidence, like small mutations that occur over time, like in E. coli, and they will then talk about macroevolution, right? And if you just imagine this happening over millions of years, billion of years, then you can easily think that a bacteria could turn into an elephant, right? I can tell you, I'm assuming you'll agree with me, Jim, that in all of science, the term extrapolation it throws up red flags in your head. Extrapolation is dangerous in science, and you always have to really scrutinize extrapolation. But to take a microevolutionary change and then be asked to extrapolate that over 100 million years, that is a wild abuse of science. Nobody else in science is allowed to extrapolate like that, to go from micro to macro. And I remember, I hate to pick on Richard Dawkins so much, but it's easy. He in one of the books or lectures of his I saw, he's talking about dogs, and he says, look, over 200 years, we've taken wolves and we've made everything from a poodle to a Great Dane to a golden retriever, all this stuff. So just imagine then, if we had 100 million years, what kind of things could evolve from that, right? And he's basically asking you to extrapolate 100 million or whatever, few million fold. And anywhere else in science, you'd be laughed at for doing that. This is just not allowed. You can't extrapolate like that. And that's what they're asking to do. So it's a bit of a bait and switch.
You know, people have asked me, do I, as a scientist, is it frustrating to see, I mean, how do I reconcile the two? When I have the Bible in one hand and I have a scientific text in my other hand, and when the two don't agree, does it upset me? And it's never upset me, not at all. I mean, even from the time I was a student, I could make a distinction between scientific fact and something that's a theory. Theories change all the time. I'm telling you, in my lifetime, this whole idea of the junk DNA. First of all, it was just slightly before when I was born that they figured out the structure of DNA. So certainly in my lifetime, so much has changed. And then you had the genome. Then you find out that the protein coding genes, the things that build us, are just a small fraction of our DNA. And then the rest was called junk DNA. And then the junk DNA turns out not to be junk at all. It's called intergenic DNA. And they're finding more and more of that, what was formerly called junk DNA, to be the traffic cops, the regulatory pieces of what directs the building of everything. So science changes all the time, certainly on the order of decades. Every 10 years, things change tremendously. And so these theories that are thrown out there, and when people say it's fact, it's not fact. There's a lot of theories. I don't see a conflict between what is written in the Bible and the science that is a fact in science. Now, I will confess that there are times that I misinterpret the Bible. I've been a believer for almost 50 years. So my interpretations of what the Bible is saying have evolved. They've changed over time. And the way I read things and the way I might interpret things. So that's subject to change as well as we study more. And this is why I like to read a lot of times the classical interpretations before many of these things came in. How did the Christian community interpret this? So our interpretation of the Bible may be wrong. It may be. And so we have to look at that. But don't let this science which put forward as fact upset you. If it's some of these things are not facts at all. Now there are facts. H2O has two hydrogens and an oxygen. Anywhere you go in the universe, it's going to be the same. Now you may have different isotopes, but it's still isotopes of hydrogen and isotopes of oxygen. So there are facts. So don't let these things upset you. Become a scientist. We need more Christians in the sciences, and we need more views on this and more looks at this and go forward with this. But what I really like is seeing your tree of life all coming from one cell, Luca, being the generation of all of these different things. And then you see the Bible said there was according to this kind, according to this kind, according to this kind, and so forth. And actually, we have a lot more evidence from high quality evidence from the biblical side. I mean, it's so interesting to see this. So to me, this has been a great scientific lesson.
Any class that taught me these criteria, these 6 criteria that I focus on here, I never had a class that really spoke to them. Sometimes they would mention that bias is bad in science and so forth. But the reason why that I developed these things is because in my work dealing with the FDA, getting a device approved for medical use, I was required by the FDA to have this very high level of evidence, which had these criteria. And then I picked up my son's high school biology book and just started reading the evidence that's in there and looking at it with that kind of lens. And it just completely shocked me that all of the things that I was held to get a medical device approved were completely disregarded in my son's biology textbook. And that kind of got me a little angry. And I thought, I got to write a book about this because this is very interesting. And so over my career, 30 years of doing research like this, I've kind of developed this filter which immediately throws up red flags when I see something on the news, like you said, that said, this is a fact, or science tells us that this is true. I have these little red flags pop up if it doesn't meet these criteria. And, in my life so far, I've never seen anything contradict God's word. There are certainly claims of that. But over time, I've found that things tend to settle down, and God's word is true.
Okay, so there you have it. You have two scientists who love the Word of God and love science, and they don't see the contradictions. And it's actually more the rookies in these subjects that see the contradictions. Those that really understand these things don't see the contradictions. Someone who never reads the Bible has probably spent 10 minutes looking at it. They'll say the Bible is full of contradictions. And I'm like, how can you do that? How can you say that? What if you picked up my organic chemistry textbook, which is 1,200 pages, and you spent 15 minutes looking at it, and you said, that's nonsensical, it's full of contradictions? I'd say, you're being foolish here. You're really being foolish. How can you take 1,200 pages that takes students 20 hours a week for 2 semesters to be able to get through, and they probably only know 50% of what's in there, and you in 15 minutes have made an assessment that this is foolish, and yet you'll do that with the Bible. You pick up the Bible, and in 15 minutes you'll say, oh, this is foolish. I mean, how can you do that? It just says that you're foolish to do such a thing. And this is what we have. And as far as these extrapolations and things that they might say in your son's textbook, this is biologists for you. As a chemist, I've seen this. I've seen it in my own life. Certainly we make claims, we make extrapolations, but we're nowhere close to what biologists do. Biologists are the biggest storytellers in the world. They'll see one little thing and they'll just project at how this has happened, and you give the sequence. And as soon as I point out, I said, that could not have happened that way because you can't bridge this step. And so then they'll say, oh, but this could have happened. And all of a sudden, they've got a different route. Just like that, at the snap of a finger, they've got a different route on how this could have happened. So it's all made up. It's a bunch of storytelling, what they say. And so don't let these things upset you. Just calm down, and the Word of God is just a wonderful document that we have given by God, and science is wonderful. That's this book of nature, and scientists hopefully get better over time, and things get refined. But to me, thank you for this presentation. This has been great. Do you want to have any closing comments here?
Oh, I just want to thank you for your time and the opportunity to present this, and also, as you said, put out words of encouragement that people pursue science, and that people hone their filters carefully, because, again, the filter that you've developed in your head determines who you are and what you believe. So that's pretty important to do that well.
Well, thank you so much, Rob, and hopefully we can have you back and doing more with us. We'd love to have you back. God bless you, my friend.
God bless you. Thanks so much, Jim.
Thank you for joining me today. If you could give us a like, share, or podcast review, we would appreciate it. If you have any questions, you could send them to ask@jesusandscience.org, and we'll try to answer some of those questions in an upcoming video. And if you do not believe in the physical resurrection of Jesus Christ, and you want to hear about why I believe, send me an email to tour@drjamestour.org, and we'll get together by Zoom, and I'll share with you why I embrace the resurrection of Jesus Christ.